So in the last units we discussed how linear systems can have multiple solutions. And what we would like to look at now is how to find such solutions systematically. Remember from unit 9.2.3, 2 units ago, that if one had this linear system right here, then one could derive this general solution right here. And the idea was that we needed a particular solution or a specific solution, which we called x sub s. And then we had this part of the general solution. This whole thing was called the general solution. And this part right here had the property that if this were a and this were xn, then a times xn was equal to 0. So this vector right here in general, regardless of what beta you pick, has the property that it maps to 0. The idea is that we need to find a specific solution, and we need to find an expression for all the solutions that map to 0. So what that means is that we also want to solve for a vector that maps to 0. And one way we could do this is to borrow from week 8 and recognize that we can simultaneously solve with multiple right-hand sides. And what we're doing here is we're making the second right-hand side that 0 vector. So let's see how we would do that. Well, we would find a Gauss transform that would take this appended system to that appended system. And we're going to put a square around the value that appeared on the diagonal. And we're going to call that a pivot. And in general, we're going to call the first non-zero entry in a row when we're done with this process the pivot for that row. I'm already starting to see that there's a little bit of a problem because these two rows are identical. So you compute another Gauss transform to place a 0 right there, and what you notice is that it knocks everything out here. And in a way that's good, because what that last row really says is that 0 is equal to 0, and at least we know that that's true. And what we're left with now are two equations in 3 unknowns. There are 3 columns here, and therefore those columns really stand for chi0, chi1, and chi2. So we have 3 unknowns and only 2 equations. And what it means is that we can't come up with a unique solution. So let's move on and do the next step that is Gauss-Jordan-like and put a 0 above here as well. And then we can do one more step. And we can place 1s on the diagonal. Remember, that was a matter of multiplying by a diagonal matrix. And all along we're updating the right-hand sides. Now, something curious that you notice is that this last column is always 0. And that shouldn't be a surprise, because at every step here we multiplied some matrix from the left, and we know that if we multiply with a matrix from the left, that affects the columns. It's like doing matrix vector multiplies with each of the columns. You all are getting very good at slicing and dicing, and therefore you understand that. And what it means is that if we start with a 0 vector there, it's always going to be a 0 vector. And what that means is that we didn't really have to work with that 0 at all. What we do need to do is, when we're all done with this process, whether we actually did or did not end up with a vector of zeros here, is we want to split it into 2 systems of equations, both of which are sort of kind of upper triangular. And for one, we want to solve with this updated right-hand side, do some sort of back substitution. And with the other one, we would like to solve for some vector, to find some vector that maps to 0. Okay, so let's see how that works. Well, first thing we're going to do is find a specific or a particular solution. And notice that these variables correspond to where there were pivots in the rows of the equations as we proceeded with our process. Chi2, as a result, is called the free variable. And the idea now is that you take the free variable and you can set it to any value you want. And once you fix that particular value, then the other values can be computed, because in this particular case there's one free variable and there are 2 dependent variables. So these are the dependent variables. Now, you can choose your free variable any which way you want. Well, we're kind of lazy. If we can choose it any which way we want, it sure is convenient if we simply choose it to be chi2 equal to 0. So let's see what happens if we do that. We choose the free variable to be 0, and then we plug it in right here. And notice that that really means that all of this disappears. And what you notice is that chi0 and chi1 are now determined by these values here. And notice that this 0 you could think of as being equal to chi2. So what you find out is that a specific solution is given by the vector 3, minus 3, 0. So what was the process? The process was to identify free variables, to choose that variable to be some value, and we recommend that you use 0, and as a matter of fact we will always use 0, and therefore it's going to be hard for you to see whether your value is the same as our value or your solution is the same as our solution, because in the end if you choose the free variable to be a different number, or you choose a different variable to be your free variable, then you end up with a different specific solution. Now what we would like to do is find a vector that maps to 0. And again, here we have 2 equations and 3 unknowns. And you would like to say, well, we again can think of this as the free variable that we can set to anything we want. And you might say, well, we just learned that being lazy was a good thing. So what if we go and we set those to 0? Well, what you notice then is that chi1 is equal to 0 and chi0 is equal to 0. And what you end up with is a solution that's simply the 0 vector, but that's totally uninteresting because of course we know that the 0 vector maps to 0. What we want is a non-zero vector that maps to 0. So let's undo all of this and instead choose our free variable to be the next most convenient value, 1. 1 is easy to compute with. So what does that mean? That means that we substitute 1 in for everywhere where there's a chi2 up here. And now we end up with 2 equations and 2 unknowns. And we can solve for chi0 and chi1. And then chi2 we had chosen to be 1. So now we have a vector that maps to 0. And then we know that any specific solution plus any multiple of a vector that maps to 0 is also a solution, and therefore this is one general solution, or one way of writing the general solution. Had we decided to choose our free variable to be some other value, then we would have ended up with a different vector here, and had we chosen our free variable to be something other than 0 when we were trying to compute our specific value, then we would have gotten a different vector right here. And obviously this is going to make it really difficult for us to test whether you did it right. So please just be consistent and do it our way, just to keep life simple. We have demonstrated a systematic method for finding a general solution. Now in this particular case, we only looked at the case where we had one fewer equation than we had variables. There are an infinite number of solutions, but notice that we only needed 2 vectors to describe them all. We needed one vector that was a specific solution, and we needed one vector that mapped to the 0 vector. If there were more free variables, then we would need more vectors. But the fact is that we're going to see in this week and next week that we need a finite number of vectors to describe an infinite number of solutions. We haven't addressed, of course, whether we have found all possible solutions. That's a topic that we will discuss next week. And in order to understand these topics, we need to understand vector subspaces and bases of such spaces. And that's a topic we're going to discuss in the remainder of this week. Before we do that, we're going to very quickly review sets.